slide. Okay, good. That screen share actually works. So, all right. So let's recap a little bit because this was pre-midterm. So we were talking about entanglement, and basically entangled states are sort of like the opposite of the independent states that we encountered in the composite systems chapter. So remember, we have a general state that might be written something like this, where you have your composite system, and you have arbitrary coefficients for all the different combinations, and then so you would write it in terms of these two labels, NA and NB. Now, independent state is always like a product form like this. So if you have a state on A, state on B, and have a tensor product, and has more specific structure, right? So this thing here, this is totally general. So any state can be written like this. So this one you can have a particular case where it's like this, but the other way is not true. So this one, there are some states, some general states that you cannot write in this form. And those states that you cannot write in this independent state form are what we call entangled states. So, it seems like, okay, it's just the opposite of independent states, which it actually really is. So just go to the next page. Right, so the example would be something like this Bell state here, this state here, where we've got something like 0, 0 plus 1, 1. And that we showed, or we just sort of did it by contradiction, I suppose. So we tried to write it in terms of a form like this. This is an independent state form, and tried to do it. And then we basically got a solution which everything is 0, and that's not really what we want. So, this is an example of a state that you just cannot write in this independent state form. And this particular example are what we actually call maximally entangled states. And for qubits, there are 4 such states. And so basically, it's like one of them is like 0, 0, 1, 1 with a plus sign, one is minus, one is 0, 1, 1, 0, and another one is same with the minus sign. And these are commonly called Bell states, named after John Bell, who we're going to talk about some of the things that he did a bit later. And these states are significant because you kind of think them as the states which are like most entangled. So the states which are least like these independent states. So somehow perhaps you might think of it as, if you think of it in terms of this Venn diagram, maybe this is not a good way to place the orange circle. Perhaps I should have maybe put in the middle, but maybe these Bell states would be sort of very far away from this independent state. So it'd be, the states which are like least like these independent states. Okay, so these are the most entangled states, and we'll actually see how you can actually quantify an entangled state. We can actually even work out a number to say, okay, this is this much entangled. So, okay, so those are the Bell states. I forget what we got up to. Maybe we got up to somewhere around here. So, okay, so what's so special about entangled states? So we can sort of start off with an example and say, okay, let's look at the properties of one of these entangled states, like this one, this 0, 0 plus 1, 1, this example of a Bell state. And what we immediately see, suppose we got this particular state, and then we got Alice and Bob, and they each made a measurement on this state. So they share this state, right? So I've drawn it sort of like these guys are very far away. They don't have to be very far away, just but this just sort of will be interesting later on. And so if they both make a measurement like this, then this is what's going to happen. Suppose actually Alice makes the first measurement. It doesn't really matter which one makes the measurement first, actually. Bob could make it first. They could make it at the same time. Wouldn't really matter, actually, but let's just say that Alice makes it first. Then what's going to happen is that, say Alice makes a measurement first, then so actually at this point when Alice makes the measurement, so after the first measurement, this branch will happen with a probability of half, and then this will happen with a probability of half. And I've written it sort of like Alice, but actually what really happens is that both of these, this is Bob's state here, and then we have Bob's state here, because, you know, these are the two terms that you have. Alice will make a measurement, but because of the way that this state is, if Alice makes a measurement, already this state will, after the first measurement that Alice does, it will already collapse or change into this 0, 0 state, okay? And for the other outcome, it will collapse to 1, 1. Now, because it's already 0, 0, when Bob goes and makes his measurement, his state is already this thing, right? It's already 0, right? So actually, with like 100% probability, so probability 1, it will become this state 0. And with 0% probability, it will be 1, because, you know, after this first step has happened, it's already 0, okay? For the lower branch, after Alice measures 1, then Bob's state is also 1, right? Then with 100% probability, Bob will get 1 because the state is already 1. And with 0% probability, Bob will get 0. So if you multiply these two probabilities together, so for example, this branch here is a half times a 1, which is a half. This branch here is a half times a 0, which is 0. This branch here is a half times a 0, which is 0. And this final branch is a half times 1, which is a half. So, okay, we did it in 2 stages, but actually this is just like what we already learned in this composite systems chapter. If we view, like, you know, these two guys as a single measurement device, then what we basically say is that, well, you know, obviously just from the way the state is written, you know, the outcome 0, 0 happens with the probability half because it's just this coefficient squared, and the outcome 1 happens with probability half because it's this coefficient squared, and then the 0, 1 and 1, 0 are not there, so the probability is 0. Okay, so so basically, you know, what we see here is that these states are correlated, right? So when Alice gets a 0 outcome, then Bob will also get a 0, okay? If Alice gets 1, then Bob will also get 1. And these things are random. You don't know if it's going to be 0 or 1, but what you do know is that if Alice gets 0, then you know for sure Bob will also have 0. And if Alice has 1, Bob will for sure always have 1. Okay, so that is clear to everybody? Yep. Okay, sorry, I don't see your video, so I'm not sure if you're nodding or not. Okay, but I hope that is clear to everybody. All right, then So let me just erase all this stuff which are in here. Okay. So the question is, okay, well, these are correlated, fine. Sometimes, when people talk about entanglement, they say that this is sort of the, amazing thing about entanglement. So is this amazing? Well, I would say that actually at this point, actually, no, it's not really amazing at all. Having some correlations is not something that's like unique to quantum mechanics. You can always have some correlations, and just to show you how you can have correlations, you can have something set up like this, where say you got two guns and then they're shooting out red and blue balls like this to each side, and then suppose like at the beginning you make sure that each time there's a blue ball going this way, you also have a blue ball, and then each time there's a red ball, there's a red ball, and so forth, right? Okay, so this will produce a pattern of correlations where basically, if you look at all the different outcomes of Alice and Bob, so 0, 0, 0, 1, 1, 0, 1, 1, and then look at the probabilities, then you'll get exactly the same kind of thing as what we just talked about, right? So the probability of getting, a red or blue ball, which is the 0 or 1. So sorry, I forgot to mention that, for example, this means 0 and this means 1, right? So the probability of getting 2 zeros or 2 1s is like half, but then you never ever get this situation where it's red or blue red, because we arranged it that way, right? That's the thing that we did at the beginning. We set it up so that there is no no chance of it going red or blue. So far, actually, this is not anything so amazing. It's just showing some kind of correlations. But there is more, as you probably can expect. So I'm sorry, okay, like this, and now let's clear the screen. Okay, but there's another trick that quantum mechanics has, which is that you can actually also measure in a different basis. So remember, well, we did it in the midterm, so I'm sure you know this, but measurements in quantum mechanics are not just like you just measure ones and zeros. You can also measure in like plus or minus basis. So we can change this knob here on that measurement machine, and then we can go to measuring in the plus or minus basis. Now, a very interesting thing happens if you measure this particular state in the plus or minus basis. And you can just work this out in a couple of lines. But basically, if you do what we've been doing for some time now, which is to say, okay, you start with this state, and we're going to measure this time in the plus or minus basis. So let's change the basis. And so, you just do your basis transformations. We've done them several times now. So I think you're starting to remember the relations. So it'd be like this, but then this has a minus sign. So if you just substitute these things into here, the formula, and then perform an expansion. So what you're going to see here is in this expansion here, this plus plus, this combination over here will also have a plus sign. So these ones will have, like, there'll be two terms which are plus plus, right? What's happened to the normalization here? I think I've messed up the normalization. I think there's there has to be an extra factor of √2 here. Yeah, I think it's 2√2 here, because there's already a √2 here, and then there's a √2 here and a √2 here. So, then there's two of these things, so it should be √2 cubed, right? So this should be √2, 1/2 √2. Okay, and then so when you look at the plus terms, these ones, there's two of them, and then so this one will be there at the end. But then if you look at the terms like plus minus, the plus and minus, this has a positive sign. This one has a negative sign, so they will cancel. So the final state that you get is like this. And so this is interesting because we've actually sort of ended up at a state that looks kind of very similar to the thing that we just started with, right? So originally started with this state 0, 0, 1, 1. And then we've done this rotation, and then there was this magic cancellation of terms, and then all of a sudden it looks very, very similar. Now, this really doesn't just always happen. This is very special property of this particular state. This particular state, it just happens to have this kind of symmetry, and it just, it just does this. So, don't think that this is, something that always happens. This is a kind of maybe a surprising and interesting result for this particular state. Okay. Then, all right. So given that, we can go and go and do our measurement. So Alice and Bob goes and does their measurement, this time in the plus or minus basis. Okay. So, well, because this state looks exactly the same, we know how exactly the measurements are going to look. So we can suppose that Alice does a measurement first, and then the actual state that she'll get is like plus plus, but well, Alice gets plus, Bob gets plus. In this case, would be minus 1 minus. Probabilities of these will be half and half. Probability of the second one here will be 1, 0, and this will be 0, 1, and then exactly the same kind of calculation. We'll get these same probabilities. So so this time, is this amazing? So I would argue that this time, this is actually a bit more amazing, because let's think about what's really happening here. So, let's go back to this kind of scenario where Alice does the measurement first here, right? So Alice is going to do her measurement first, and then Bob follows up later. So what this means is that Alice could just decide at the very, very last minute of whether to do the measurement in 0, 1 basis or the plus minus basis. Okay. So she could just, just decide, just last minute go, okay, this time I'm going to do plus 0, 1. And if she chooses 0, 1 basis, then Bob will get either 0 or 1, depends on what she gets, but Bob will get 0, 1. But if Alice chooses the other basis, plus or minus basis, then Bob will get plus or minus basis, right? States. Okay, these are also random, but these will be the states that we get. And and this is where it's important that these guys are separated by a long distance, because what quantum mechanics is saying is that this process actually happens instantaneously, and that means faster than the speed of light. Okay, so if Alice makes this measurement, then Bob will actually get these results before any kind of light signal could propagate. So it basically means that suppose Alice sort of accidentally, there's also like some kind of communication channel here that's telling Bob if it's the plus or minus basis or the 0, 1 basis, right? So if it were possible to do this, then, perhaps the universe is conspiring against you, and you can, the machine kind of figures out the right state to make, right? But if this can happen faster than the speed of light, then there's basically no way that you can even cheat and kind of, have that situation where these machines are, going to produce the correct type of states. So so basically this is really very weird, because apparently there's this kind of correlation between Alice and Bob that is happening faster than the speed of light, and it seems like you're doing something that's actually kind of impossible, because well, we know from Einstein's theory of relativity that basically nothing travels faster than the speed of light. And so this is what Einstein was saying to be like this spooky action at a distance. So Einstein said that basically nothing can travel faster than the speed of light, yet it kind of appears that quantum mechanics has this ability that that Alice, who is very far away from Bob, can actually affect the outcome of Bob, basically purely based on her choice of measurement. So Alice's just choice of, okay, I'm going to do 0-1 basis or plus minus basis. Somehow that information seems to get all the way to Bob, and it can do so faster than the speed of light. Hence the spooky action at a distance. So it's action at a distance because basically seems like you can affect things which are very far away from you, even though basically nothing actually travels between those 2 points, right? So there's not even light can actually go between Alice and Bob, basically because it happens instantaneously. There's no particles, there's nothing between them, yet you can affect the outcome of Bob. All right. Any questions?
Like what if Alice chooses for example like 0-1 basis and Bob chooses plus minus basis at the same time?
All right. Yeah. So yes, that's a good question. I didn't quite explain that, but basically in that case you can't really see the correlation. So hold on, let me just go back to sharing the screen. So, okay, so let's just quickly do that calculation. So suppose we can just do it from here. So you said Alice does 0-1 and Bob does plus minus. Is it that way around, or? Okay, well, I guess it doesn't matter. So let's just stick to that one. Okay, so let's just work out what happens when Bob does the plus minus basis instead, right? Okay, so the first step is going to be the same, right? So first step, Alice is going to measure 0-1. Okay, so let's just write that here, 0-1 basis. And then so after the first step, what happens is that Bob will get the state 0. And over here, Alice measures 1, and then Bob's outcome will be 1. All right, and then instead of measuring in the plus or minus base, in the 0-1 basis, we're going to measure in the plus or minus basis here. Now, we know what happens when you have a state like 0, and then you're going to measure in the plus or minus basis, because 0 can be written as plus state and then minus state, right? And so, okay, so it's maybe getting a bit messy. So let me Let me rewrite it somewhere else. Okay, so all right, so basically, okay, so we're starting in the state 0, 0 plus 1, 1. Okay, so 1 square root of 2. Okay, and then after the first step, basically the state becomes 0, 0 or 1, 1. These probabilities are half. Now, because when you do, when you have a state 0, because it can be written as plus minus, then that means that with the state 0, it will become, if measured in the plus or minus basis, it will become plus or minus with a probability of half. Okay, so if you, and then for the other starting state, if you start with 1, then this will become plus or minus, also with the probability of half. So basically what this means is that the 4 outcomes that you're going to get are like this. So you're going to get 0 plus state, and then 0 minus state, and then this will be probability half, 1 plus state, 1 minus state, and this will be probability half. And so basically the probability, the final probabilities of these 4 outcomes are going to be all a quarter. So in this case, you don't really see the correlations, mainly because you're not really measuring the right basis to see the correlation. So this state here, the correlations are sort of in the 0, 1 basis, I guess. So unless you measure it in that basis, you kind of don't see it. So you just get a quarter everywhere. But if you measure in the 0, 1 basis for both of them, then you do see correlations. If you measure in the plus minus basis for both of them, then you also see correlation. Okay. All right. So any other questions? Okay, no. Right. So this is definitely a very weird aspect of quantum mechanics, and it kind of looks like you can do something very useful, which is so-called superluminal communication, right? So superluminal means faster than the speed of light. Okay. Now, what I just told you is that, depending on what Alice does, measures in 0, 1 basis or measures in plus minus basis, this will affect the state of Bob. And it happens instantaneously, right? So, this looks like you could do something like, okay, so, these guys first, prepare an entangled state, and then perhaps you can encode your information as the basis that you are choosing, right? So if Alice wants to send a message, and then, so it's just some bit string, like, 0, 1, something like this, right? So basically what she would do is, like, if it's a 0, then she measures, say, in this basis. And if it's a 1, she measures in the plus minus basis, right? And then all Bob would have to do would be to say, he doesn't even have to know, or, it doesn't really even matter what state it is, right? Like, it could be 0 or 1. Doesn't really matter. It's actually the basis that we are trying to encode the information in, right? So these are the, that the information itself becomes like the basis, actually, right? And then what Bob has to just be able to tell is, okay, so which basis did Alice choose, right? And then if Bob could do that, then we have a way of doing superluminal communication, and that sounds really awesome. Now, there's a unfortunate kind of fact that unfortunately that just doesn't work. Okay, unfortunately, it looks like it might work, and basically the reason why it doesn't work is that basically these things are random, right? So even though like 0, 1, and then plus state, minus state, they're physically different states. Okay, so they're definitely different physical states. They are sort of definitely kind of it's not like those are kind of sort of the same or something. These are definitely different physical states. The unfortunate fact is that each of these ones, like the 0, 1, they occur with the same probability, half and a half, right? And this one also occurs with the same probability, half and a half. And if you go and actually calculate any kind of observable, and ultimately it's got to do with observables, because what can Bob do except for try to construct some observable to figure out what basis Alice chose, right? Because observables, that's basically the readout of the experiment. So if you actually go and calculate the expectation value for this situation, then what you'll find is that on average, these things will all be 0. And then if you calculate the expectation value, again, all the averages will be 0. And then eventually you have no signal. There's no way to actually distinguish it, even though they're sort of physically different. This randomness, you can think of it as noise, just kind of washes out the signal, and then you just cannot get it. So let me just show you exactly what happens if you actually calculate these expectation values. So let me just get rid of these lines. All right. So for example, suppose Alice gets 0. So in this case, if Alice gets 0, then Bob also gets 0. Okay, and if you calculate 0, expectation value 0, does anybody know what that would be?
Zero.
Yes, that is 0, because if you remember what the action of X, so the X matrix is like 0, 1, like this. X kind of flips the spin, right? So X acting on 0 becomes 1, and then it's like inner product of 0 and 1, and then that's 0. Okay, and something similar happens for Y as well. So 0, Y is 0. Now 0 of Z and 0, what about this?
It's still 0.
So let's just stick to purely evaluating this thing. So remember, Z acting on 0 gives what?
0.
0 0 state or 0 number?
And cat, yeah, state.
Yeah, cat 0. Yes, exactly. So in other words, this is 0, 0, and this gives 1. Oh, okay, it's 1. So why did I just say it's 0? Well, it's because, so for this outcome, if this was the only one that happened, then that would be fine. But that happens 50% of the time, right? And then 50% of the time, you get 1, right? And then for the one case, so Bob will also get 1. For the one case, expectation value of one state of x, what does that give?
Zero.
Yes, this one is 0. Okay. Expectation of y with one state is also 0. Expectation of one state with z, what is that going to give?
-1.
Right, exactly, -1. Because z acting on one state gives -1 times that. So because so if it was just only zeros that are coming across, that would be great, right? Because we'd have expectation value of z is 1, and well, that's our signal, right? Oh, we got z equals 1, great. But then the problem is that the other half of the time, when you measure 1, and you can't control this, it's random, then z will be -1, okay? And then if you average 50-50 with +1 and -1, then you get 0. So that's why z is actually 0 in this case. It's not because actually the individual expectation values are 0, like these cases, right? So in the x case and the y case, you know, the expectation values for that particular state was 0 anyway. But here it's not the expectation values like that are 0 actually. It's the fact that it's 50-50 these two states, and you can't control them, right? And then so when you average over everything, it eventually becomes 0. Now for the something similar sort of happens for the plus-minus case. Now for the plus state, if you calculate that, does anybody remember what the expectation value of that one is? Plus state expectation value with the x operator. Maybe not. Okay, all right. So if not, let's just quickly work it out together. So plus state, remember, is defined as 0 plus 1. Okay. And then x acting on plus. So what that does, x, remember, is like something that flips the spin. So changes 0 to 1 and then 1 to 0. So this one becomes 1. This will be 0 state. Actually, so it's actually the same state. Okay. So x acting on the plus state just gives plus. And eventually, so this one will be plus in a product with plus. And then what's that going to be?
It's 1.
Yes, because it's a normalized state, so it's equal to 1. Now, if you calculate minus of x minus, then evaluating x on minus state. So this minus state is just the same thing with the minus sign here. So what this does is to, again, it flips the spins. So it'd be 1 minus 0. But actually that's got an extra minus sign because remember, because minus state here actually is 0 minus 1, and this one is 1 minus 0. So this one will actually be minus state. Okay, and then so this one will be minus of minus in a product minus, and then this one will be minus 1. So what's going to happen here is that, again, so if Alice gets plus, Bob will get plus. Alice gets minus, Bob will get minus. But they happen with 50-50, right? And then when you average over these two cases, so this case and this case. When you average over those two cases, again, x will be average, overall average of x will be equal to 0. And for these other ones, what you can work out is that, well, we can just quickly do it together, which is that if you calculate z on plus, then this is z acting on 0 plus 1, and then z will produce a minus sign on just the one state, right? That is actually the minus state. So if you calculate what average value of z is, then what's going to happen is plus inner product with minus state. And what's that going to be?
0.
Yes, they're orthogonal states, so these are 0. So basically, it's sort of like, you know, what happened to z in the first part here is going to be like the similar situation to the x things, right? So these two were 0 because like kind of they're really 0, like, you know, every state is expectation value 0. This one happened because of this averaging effect, right? Whereas in the plus minus one, the x one is the one that's a bit like this one, and then the y and the z are the ones that are sort of genuinely 0, if you like. But basically, either way, everything is 0, and so Bob actually, even though, well, you know, maybe it's there's an interpretational kind of aspect to it, but you know, at least in this Copenhagen type of interpretation, even though, you know, physically what really happens is that Bob will either get 0 or 1 or plus minus, and even though those are physically different states, somehow because of the randomness, Bob just cannot tell the difference which one happens, and basically you cannot do superluminal communication in the end. So unfortunately, it looks like we're very, very close to be able to do it, but somehow you just can't. And it's a very weird fact of quantum mechanics that, you know, even though actually, you know, Einstein's theory of relativity and quantum mechanics are kind of developed completely independently, right? So when Einstein was trying to work out his theory of relativity, he did not, you know, he was not really, you know, thinking, or he didn't really include quantum mechanics into the theory. And likewise, quantum mechanics doesn't really include, well, general relativity. There's actually still no theory that you can, you know, merge general relativity with quantum mechanics. But even though they're basically quite different theories, they're sort of consistent, but they're consistent in this very surprising sense, because, you know, in the end, they basically, you know, even though it looks like there's a spooky action at distance, it actually, there's no information that you can convey, and there's nothing you can do with it, which is a very, very kind of a peculiar thing that happens. Yeah. Any questions there? So occasionally, you know, every sort of few years, every few decades, somebody comes out with a paper saying that they can actually do superluminal communication. And generally what happens is that, you know, they've maybe made a mistake somewhere, or some hidden assumption or something like this. And in the end, it just doesn't work. But yeah, it's still, it's kind of, it's, you know, looks tantalizingly close that you can actually do it, but you can't. Okay, all right. I guess you guys are. Oh
like,
yeah.
like why, like if why does the average of xy of the qubits of 0 means that Bob cannot actually tell which.
Right. Yeah. So okay. So yes, that's good. I didn't maybe properly explain that point. Yeah. So yeah, it's not so much that you want it to be 0 or any other number actually. What's important is that there's a difference between these two cases, right? So you basically want a signal to say, aha, Alice did this one, or Bob did this one. Yeah. And so to have a signal, you need some difference in some observable between these two, right? So say if this number was different to this number, that would be good enough, right? So say in this case, Z was 5. Okay, it can't be 5. Say Z was 1, right? If Z was 1 here and Z was 0 here, that would be great, because then you go, well, average value of Z is 1, so I can tell that Alice did this one, right? Bob just needs any signal that just points out, gives any kind of indication, any kind of difference between these ones. But unfortunately, there's no difference in any of them. So Z is 0 in both cases, Y is 0 in both cases, X is 0 in both cases. And so because there's no signal, there's nothing that you can kind of use in order to tell what Alice did.
Yeah.
If we choose different observables, it will also be the same.
Well, for a qubit, actually, there are no more observables. So X, Y, Z are the only observables that you can actually make. It goes back to the fact that for a qubit, there are only 2 degrees of freedom, right? For a pure state, at least. So there's theta and phi. And so in fact, actually, maybe, if you're talking about pure states, there's sort of you only need 2 observables. So maybe even X and Z or something like that is enough. But normally, like later on when we do like mixed states, we'll see that you more generally need 3. But yeah, those are basically the only observables that you can make. Any other observable you can construct out of those. So basically, there are no more observables. Yeah. I mean, that brings up another question of, okay, well, maybe for a qubit it doesn't work. How about for maybe a bigger system? Maybe there's more observables, and there would be some other way to tell. So people have tried stuff like that, and yeah, basically still nobody can find anything.
Yeah, so it's like although we kind of know that they should be correlated, but we cannot actually use it to do anything.
Yeah, exactly right. Yeah. But actually, we will see that there is a way to actually perhaps not do something so much like what I was describing, but there is a way to tell that there are more correlations in this quantum system than the classical. So you can do that. So in fact, I think that's more or less the next topic. So, okay. But yes, at this stage, that's correct. Okay, so yes, that's exactly the next topic. Well, okay, we'll do a little bit and then can continue probably next lecture. But so yes, so Bell's inequality. So I showed a picture of John Bell before, and so this is named after him, and basically, so people kind of knew even from this Einstein's time that there is these quantum states seem to have like more correlations than available in classical physics, but then nobody could really sort of actually quantify it or try to really understand or have a way of putting a number to it basically. And eventually what John Bell did was to kind of figure out a way of showing these types of stronger than classical correlations. And it turns out that actually there's this eventually leads on to being able to rule out one of the interpretations of quantum mechanics that I listed in one of the previous slides. So if you remember that, one of the interpretations of quantum mechanics is that the wave function is maybe like some kind of representation of the knowledge you have of the system, right? So I gave that example of the airline that crashed in the ocean and there's a circle. The airplane's somewhere in that circle, but you don't know where. I mean, physically, it's definitely somewhere. It's not like, there's a superposition or something like that. It's really somewhere. You just don't know where it is, right? And so there was that kind of interpretation of quantum mechanics. And this Bell's inequality eventually helped to show that interpretation just is actually impossible. So this is the situation that Bell considered. Okay, so Alice. So we got Alice and Bob again. Oops, where am I going? Okay, so we got. How did I end up here? Okay. All right. So we got Alice and Bob again. And again, they have a measurement device. And we're going to deal with qubits again. So we've got this 2 qubits. One of them is going to be measured by Alice. One is going to be measured by Bob, just like what we were talking about up until now. And these particles are going to be measured. And these measurement boxes, they have 2 settings. And so they make the 2, these guys can change the settings of boxes, and there will be a readout of like the spin, and there's only 2 values of the readout because these are qubits. Okay, so these are qubits, so there's 0 and 1, or okay, I think I wrote plus and minus. Okay, and that's the basic setup that we're going to kind of consider. So, right, and what we're gonna, so that's, well, okay, so that's the quantum version of the setup that we're gonna consider, where we have an entangled state in the middle here. So we've got some entangled state and there's some quantum measurement device. But we're gonna first also consider a kind of a classical version of it, I guess, and same basic setup. So suppose you just have regular classical particles, and a bit like what we had with that gun shooting red and blue balls. So you have some source, and maybe there's some correlations between these particles that are going in there. But the basic setup of this in this classical version is going to be the same, where we've got like 2 settings in the boxes, and then we've got 2 outcomes, 0 and 1, and and basically what's important in this kind of way of thinking is that, you know, what we're going to basically make any judgments purely based upon just the outputs of these boxes and then these input settings. Okay, so we consider it to be like a kind of a black box, and even though I replaced it in this case with like a classical source where there's, you know, these correlations, or it might be like a quantum source or something like that, you know, basically we're going to make all our sort of assumptions, you know, sorry, no assumptions. We're going to basically make all our sort of arguments based on the fact that we've just got these two settings, we've got these two outputs, and, you know, what could possibly happen with this situation. So, you know, we're not really going to put really any physics actually into this. We're not going to like model the nature of the particles. You know, we're not going to even say what the balls are. We just purely going to make statements based upon, you know, the outputs of this box and then these measurement settings. Okay, so this kind of black box situation where you don't know the contents of the box, you just only know the outputs, you know, what's on the outside of the box. So John Bell then basically asked, okay, so, you know, suppose I wrote down some classical probability distribution, right? So first consider that somehow this is classical, and, you know, don't worry about any quantum mechanics. So we just got a classical random kind of system, and with this kind of setup with two settings and then two outcomes, what is the maximum kind of correlation that I could possibly observe with like a classical probability distribution? So to basically set up this problem, what he did was to say, all right, well, you know, let's just make this completely general. We're not going to like model the balls by anything or anything. Let's just write like the most general probability distribution that you probably have. So what he did was to say, all right, well, we're going to have some correlation. So we're going to have some, you know, this probability distribution, but it's going to be dependent upon this kind of hidden variables, and actually maybe more than one variable, maybe a lot of variable, infinite number of variables. And all those variables represent like, you know, whatever model that you would like to choose to, you know, model this potentially, right? So we're not going to really make a model, but we're just going to make a completely general statement about probability distributions and this situation where, you know, you've got these two outputs and then these particular knobs that you can change. So so for example, in this lambda case, you know, if our model was like this simple, then actually we wouldn't need so many variables. So for example, this lambda here, you know, if we're going to model with like a red or blue balls or something, we would just have like some, you know, binary variable to say that, you know, all this, the output of the boxes is controlled by, you know, whether the ball is red or blue. So that would be like just a probability distribution with, you know, like a binary variable, right? So this lambda would be, say, you know, two variables, 0 or 1, and, you know, 0 means red and 1 means blue. But, you know, we could have a much more complicated model than that. You know, say there's like, you know, lots of different colors. There's red, blue, green, yellow, and all these different colors coming. And, you know, what these boxes do is something more complicated. You know, if it's like a yellow ball, it does this, and it's a green ball, it does this, it's a red ball, it does this, blue ball does this, and, you know, who knows like what very complicated situation you can possibly create. So let's just, you know, to capture the most general case, we just have an infinite number of variables, lambda, that controls the sort of the underlying, physics of the actual situation. And let's see if we can make any statements based on that. So basically what we are going to do then is to see, whether even with like an infinite number of variables, we can reproduce the same kind of statistics that we have in this quantum mechanical situation that we have here. Okay. So right. Yeah. So maybe we'll just leave this one as the last slides. But the kind of observables that we're going to have are like this. So for example, so we've got our underlying, probability distribution here. So, whatever your, classical, complicated model with an infinite number of degrees of freedom is. And basically our outputs are going to be some kind of function of this underlying variable, which we're going to call the hidden variable, because we don't know what's really happening in the system. And so whenever we have particular observables like this, there's some kind of mechanism inside the box that converts, say on setting 1, so say the switch is put on setting 1, then this A function gives basically the rule for whether so for this particular case, say if it's a blue ball, then the value that it's going to give is going to be +1 or -1. Okay. Say for a blue ball, for a red ball, it's going to be +1 or -1, yellow ball, green ball, and some complicated set of rules that will tell you, okay, if it's a red, blue, green, orange ball, it's going to be like +1 or -1. And so the average value of that will be, of course, just given by this. Now this B thing is the same thing for Bob. A dash is like for the different setting. So for a different setting, there might be a different rule to find the average, and B dash will be like the different setting. And all these variables, basically each of these outcomes are always like +or -1. So that's why these variables also are going to be +or -1. Okay, so I don't know. I think we're just about to come to the punchline. So I'll just tell you what the punchline is. But so the punchline is that using this very general argument, Bell, and then later on improved by these guys, Clauser, Horn, Shimoni, Holtz, CHSH. These guys proved that you can actually, under very general probability distribution, it should always follow this kind of rule. And what we're going to see is that actually with quantum mechanics, it's possible to actually break this bound. So it's possible for this left-hand side to be actually bigger than this value of 2. And that eventually shows that the quantum mechanics, basically, certainly it does not follow this kind of hidden variable rule, and essentially shows that there's more correlations in a quantum system than a classical system. But okay, we can talk more about that next week. So any questions? Nope. Okay. Then, oh yeah, as for homework, no homework this week because you guys did an extra one, and so you did the midterm, so don't worry about homework this week. But I guess we should start really thinking about the assignment projects. So yeah, perhaps let me know by email, those of you who haven't told me what you want to do, and I think we should start setting a date for presentations for that.